Okay, so now we are in the second part of the week 11 worksheet, which is the quantum tunneling and wave packet. So notice that we've set the potential to be constant because we just want to look at normal boring wave packets. And we can watch it evolving in time, and it can be helpful to put on the phase and to potentially also see the magnitude. Oops, sorry, I clicked the wrong thing. And we can restart. So the first question is what the green band represents. And if you just look at the simulation and don't know anything about it, it's hard to tell. But what I can do is pause and restart, and I can try adjusting this green band and notice what's happening to my red curve. It looks like my red curve is actually getting wider and narrower, which would correspond to the average energy changing. And we know that it's not just one single energy here because it's a wave packet. It must be the superposition of many different energies. And in fact, if I go into configure energy, notice that the statement is average total energy. And so I say in question 6 to set that to be equal to 1. So we do that and hit apply and close. Now, the other thing we can do is notice that I can start to say something like, what is the initial width? And as I adjust the initial width, the green band does appear to be changing. And we've already learned that there's a relationship between the width in space, and then we could talk about the width in k-space, which relates to momentum and energy. So this is all very self-consistent. So the first question says, question 6 says to set the initial width to be 0.5, which I've already adjusted that. So let's put that on 0.5 nanometers, and the initial position to be -6. There we are. Then let's look at the real component, again, the red, and watch if the wave packet width is changing in time. And again, we're looking at the envelope. And very clearly we see that the envelope is spreading out. And so we can say, what does that mean? We can see, in fact, that it doesn't just initially happen and then stay the same. It's kind of constantly spreading out. And it's a little bit difficult to really make a measurement of that. But again, we don't see a behavior where it spreads out, bunches back up, and spreads out again. We see that it seems to consistently spread out. The second question is whether the wave packet envelope is moving to the right at constant speed. Is it speeding up, slowing down? This is a little bit difficult to see. I'm actually going to turn this off and let's start. And actually, it doesn't really matter whether we look at the top or the bottom. I've actually tried to pause this. We really want to look at where the peak is, right? And so I've tried to pause it, and it does appear to be moving at a constant speed, which is what I would expect. And if you think about your group velocity, the group velocity is going to relate to the average momentum. And so if you have a constant average momentum, which we do because our energy distribution does not change in time, then we would expect, in fact, our group velocity to be constant, and it seems to be in the simulation. The next question is, what about the little oscillations inside the envelope? So now let's turn this back on and watch these again. So the question is, which is faster? And you can kind of see that the black envelope catches up the peak of it to different oscillations, which means that, and it's easier to see at the very beginning, right? It's catching up to this one, and now the peak's at that one, and then it's at this one. So clearly the envelope is moving faster than the little oscillations on the inside. The little oscillations are moving basically at the phase velocity, so we say that our group velocity is faster than the phase velocity, and the books talked about the fact that it's twice as fast, that mathematically we can see that. So then we can ask, is the integral under the curve of probability density staying the same? Because we see that that peak is decreasing. Now, if you just observe it, the answer is, well, I don't know, maybe, right? It's difficult to integrate by eye. However, we know that your probability density, if you integrate over a region, that's going to tell you the probability of finding your particle. And the answer is we have to find our particle somewhere. So as this spreads out, this just means the area over which we are more likely to find our particle is increasing, but that integral always has to be equal to 1 because we always have to find the particle somewhere. So even though it's a little bit difficult to judge by eye, you see that as the peak is decreasing, it's getting wider, which means that the area under the curve could be staying the same, and mathematically it must be. That is literally what probability density relates to. So now we're going to increase the initial width of the wave packet to 3 nanometers and leave the other parameters the same. And the question is, what else is changing? So we see that the probability density maximum amplitude has decreased, and that's because it's now spread out over a wider area, and we've said that the amplitude needs to stay the same. We also see that our green band has changed. And again, there's that relationship between our uncertainty in position and our uncertainty in momentum. So since this is a Gaussian wave packet, decreasing the uncertainty in momentum, or energy here, corresponds to an increase in uncertainty in position, which is what in fact we see. Now let's play it forwards in time. One of the things that you also notice is that this seems to be fairly constant now in time, right? So you don't see that this wave packet is spreading out as much. And what's happening here is that because this momentum distribution, this energy distribution is more narrow, that difference in momentum is what causes your wave packet to spread out. So since there's now smaller differences between your momentum components, that means that the wave packet doesn't spread out as much in time. It is still spreading out slightly. It's a little bit difficult to see that, but it isn't as dramatic of an effect as before. So the three things that we can see, changing in the simulation then are kind of this band up here, the wave packet width, and then in a way how this is spreading out. And so this is what I've been talking about, this relationship between our distribution in X, our distribution in momentum, which we have to infer from the distribution in energy. But the larger the distribution is in momentum, the more quickly that wave packet's going to spread out in time. So this is a small distribution in energy or momentum, and therefore that wave packet staying much more similar. And a way we can think about this is the plane wave is in fact the limiting case where there is one specific energy or one specific momentum, and there's basically no wave packet here. It just fills all of space, but that also means that your wave packet width isn't changing. Your wave packet width is basically infinity, and it permanently stays infinity. Okay, so now let's go and make a quantum measurement, and let's do it on a wave packet. So if I make a quantum measurement right now, we see that my nice wide packet became this delta function. Okay, and I'll just, let me not actually do that, and I can play it forwards. So notice that green band here, what that looks like. It's kind of narrow, and it is going off the top of the screen. We can't see it. When I make that quantum measurement, it gets much, much wider. So this is really important. So what we're measuring here is position. Notice how narrow this distribution is. And if I play it forwards, we see that it spreads out. Now, if I make another measurement, we now see, okay, it's narrowly here. I play it forwards, I make another measurement, it's narrowly here. So it's always very narrow. And the idea is this is as close as the simulation is going to give us to a delta function in position, and a physical measurement of position would have some width associated with it. But then we see it evolve, and the reason it's going to evolve the way it does is we have this incredibly wide energy distribution. And this is what has to happen in your Fourier transform. That something that is a delta function in position would basically be an infinite distribution in momentum, every single momentum component. But in fact, it isn't going to be a perfectly symmetric distribution. We aren't going to have exactly every component. And so you get that sort of quick spreading. And notice that here you have components both to the left and to the right. Again, that is what would happen if you had something that looked like a good delta function. So really thinking about this Fourier transform, that we can go back and forth between a delta function in position, which gives you a very wide distribution in momentum, which gives you a wide distribution in energy, versus a plane wave, which gives you this incredibly wide distribution in position, and then a very narrow energy or a very narrow momentum. So I hope that makes sense. Again, a nice way to really see how things are changing in time, how that relates to all of these different properties we're talking about, and ideally how this then relates to the uncertainty principle and Fourier transforms.